We are in the second part of the theory of adhesion. We will see wetting and the difference between the work of adhesion and the work of cohesion. We have seen in the first module of the theory of adhesion that if the adhesive is applied in the liquid state, then we are all right. It will wet the substrate. Well, not exactly like that. We will see that it's more than that. Also, in this module, we will see the difference between the adhesion and the cohesion work. This is very important to understand that in good conditions, if we surface treat properly the surface, then we should always have cohesive failure and never adhesive failure. Okay, so let's start with then wetting again, and with the fact that it's not because it's liquid that necessarily it will wet the substrate. And you have here a very, very nice example. You know that in nature the water does not always spread uniformly on the surfaces. Here it's very clear that it forms a spherical droplet. We can look at that in more scientific terms and look at the contact angle, this theta, between the liquid and the solid. And this theta in fact varies quite a lot. It varies from 0 degrees to 180 degrees. Of course, what we want ideally is 0 degrees where we have a perfect wetting. This is fantastic. Worst case scenario is this, where we have a spherical droplet. This is what we have here, spherical droplet. In practice, this probably marks the limit. Less than 90 degrees, in general, it works. With a bit of pressure, we can force the adhesive to wet. I did a demo in the previous model where I put a drop of the cyanoacrylate, and you saw that with pressure, it wet very easily the substrate. So less than 90, it is reasonable. More than 90, we are in trouble. 0 is the ideal situation. This theta, this contact angle, also comes into this very famous equation, the equation of Thomas Young, more than 200 years, this equation, which relates the energy of the solid with the surface or the interface energy solid liquid and the surface energy of the liquid with cosinus theta, so that it is in this line. But what is the surface energy really? What does it mean physically? Well, this is related to the unbalance of attraction forces at the surface. Let's look at this scheme below. You have these atoms and molecules that are in perfect balance because the forces are in equilibrium in all directions. They are very comfortable, the molecules and atoms that are inside the liquid. Whereas those that are at the surface, they are not. There is a force that pulls them down. They are not comfortable. You need an extra energy to be at the surface. That's that energy we are talking about. It's like they are being under tension. We also call surface energy surface tension. This extra energy of the atoms of the material that is at the surface is very clearly seen when we have a liquid. For example, certain insects can float at the surface because of the surface energy. Also, clips can stay at the surface because of the surface energy. You can see very well how the water, the surface of the water is being bent underneath the clip. And we can also do that here with a small demo. I have here a recipient. It's full of water, and I'm going to put a needle on top. And I'm going to show that the needle is going to stay on top because of the surface energy of the water. Before I put the needle, I put a small piece of paper so that the needle will contact perfectly parallel the water. So the paper will go down and the needle will stay at the surface. That's the plan, at least. So I put first the paper, and then on top of the paper I put the needle. and the needle will stay at the surface, and the paper slowly will move down, and you will see how the needle can float at the surface. So let's move on, and let's see now adhesion cohesion work. I want to prove basically with the next few slides that the adhesion work is higher than the cohesion work. That means it should never fail at the interface adhesive substrate. Okay, so what's the work of adhesion? Well, by definition, it's the energy of new created surface minus the energy of the interface destroyed. Schematically, we go from this situation, okay, to this situation. Here it's bonded, here it's separated. So the energy of new created surface, it's surface energy of the liquid, surface energy of the solid, and the energy of the interface destroyed. It's this energy, the energy of the interface solid liquid. I remind you that a surface is a region between a condensed phase and a vapor phase. So you have here a surface, you have another surface here. What's an interface? Region between two condensed phases, between liquid and solid. For example, here you have an interface. Mathematical terms, what we just said is this: the work of adhesion is equal to the surface energy of the solid plus the surface energy of the liquid minus the surface energy or the interface energy. Very good. But there is something that is very extremely important, in fact, and makes the whole difference. That's the spreading pressure. The surface energy of the solid is not the same whether it's in vacuum or in normal condition. Normal condition, you will have a film of adsorbed water, and this changes slightly the surface energy of the solid. And the difference between this situation and this situation is precisely the spreading pressure, the difference between the surface energy in vacuum and the surface energy in normal ambient conditions. By the way, adsorption, what is this? Is the fixation of molecules of vapor or liquid at the surface of another substance. Okay, so let's go back to the work of adhesion, and now we need to update with the expression, the previous expression, this one, to take into account the spreading pressure. So this goes into this, and we are left with this new updated work of adhesion equation. Very nice, and it's very clear that this in equation we have the surface energy of the solid, and this can be substituted by the Thomas-Young. We have seen it's equal to the surface energy of the solid liquid plus surface energy of the liquid times cosinus theta. So if you substitute this by this, you are left with this equation where you only have the surface energy of the liquid and the contact angle and the spreading pressure. Okay, what do I do with this? Well, the objective, I told you at the beginning, is to compare work of adhesion with work of cohesion. So let's see now what is the work of cohesion. Work of cohesion is very, very simple. It's simply the energy necessary to separate two identical surfaces. So we want to go from here to here. It's simply 2 times the surface energy of the liquid. Very, very easy. Now, how do two compare now? How is the work of adhesion versus the work of a cohesion? Well, let's take again the equation for the work of adhesion, but now let's assume that we have good conditions. We created good conditions for a good wetting. What does it mean? We surface treat and the adhesive will spread nicely. So we can assume in the limit that the theta is equal to 0. So this equation simplifies, and the work of adhesion for very nice condition is simply 2 times surface energy of the liquid plus the spreading pressure. Okay, but previously we have seen that the work of cohesion is 2 times the surface energy of the liquid. So how do they compare then the two? Well, the work of adhesion in fact is higher than the work of cohesion, and the difference is the spreading pressure. So I told you when we introduce spreading pressure, it makes the whole difference. That's here the proof. And with this, we prove that the work of adhesion, with good conditions, we surface treat properly the surface, is higher than the work of cohesion. So if you treat properly a surface, you should never have a failure at the interface. That's what it means. So it's really a very important result, this.